All right. Good afternoon, everyone. Welcome to our bi-weekly seminar, Viceroy Sizer Seminar. This actually happens to be the very last seminar we have for this spring semester. I know it's a very busy time of the semester. In just a couple of weeks, you will be doing your finals. I trust you are doing well and finishing strong with the semester. This was also busy because just last week, a good number of us, our group of students from WSU went to the Viceroy Symposium last week at William and Mary. We had the competition won by our outstanding team of students. So congrats to that team. It was a lot of fun to see on the first day to kick us off with a big win. And then there were also two teams of Sizer students who had their posters presented on the second day of the symposium. So it was a great time to hear from leaders in the Viceroy program, DoD operators and colleagues and students from a large number of universities across the country. And so that's one of the reasons. And then when they are back again to finish up with the school work and the rest of the semester. So I'm very proud of what happened at the symposium and generally on how you're doing. So today in our round of seminar, we are finishing on a high note. And I have the great pleasure of introducing today's speaker, Dr. Leon Lee, who is an assistant professor at the School of Electrical Engineering and Computer Science here at WSU. Dr. Lee, he joined WSU just this year, and he comes from having done his undergraduate degrees as well as graduate degrees, his MS and PhD in computer science and engineering from University of California, San Diego. And so all of his degrees are from there. Hendy works in an area that I am very excited about hearing today in hardware security. That's his main area. He would actually be teaching that course once he settles down here. For the coming semester, he would be not teaching a security course, but some other things. And the topic is exciting because we are devoting some time to hardware security, but specifically in there about IP protection. IP is intellectual property and the hardware aspect of it in the context of a fully transparent world, reliability solutions for this. And he's got a take on it that is closely tied to his research. And I'm very much looking forward to what he has to share today. So you know the deal, you would follow along. And if you have questions, you can put them in the chat. I will be monitoring them and Dr. Lee will answer the questions at the end. Or you can save your questions towards the end and then he will leave some time for addressing those. Other than that, there will be a few minutes before the end where James would give you the link and he would give feedback for the seminar. So pay attention and follow along. I don't think I have any other things to say. Thank you very much again, Leon, for taking the time, and we're looking forward to your presentation. Take it away.
Of course, it's my great pleasure to be here. And first of all, I'd like to say congratulations to all of the students for their great accomplishments. So I'm gonna end this semester's talk with a dive into some hardware security and reliability issues. So we know that nowadays a lot of companies are designing their chips, including some traditional software companies. Google, Microsoft, they're all getting into this chip design game. So in this scenario, they used to protect their software intellectual properties, but nowadays they're putting heavier emphasis in protecting their hardware intellectual properties as well. In the meantime, reliability has always been a concern for hardware designs, simply because hardware is really the root of trust. It gets integrated into every system, ranging from robotics to military defense applications, and reliability is of utmost importance. And today I'm going to talk about security and reliability in a fully transparent world. So what do I mean by a fully transparent world? It carries really two meanings. For one, chip design and manufacturing is a very complicated process. Nowadays, it's very difficult to do that by a single company. It really happens in a globalized supply chains where one company handles the design, another one handles verification, and then manufacturing and testing will be outsourced to some other countries, some offshore foundries. So this gives us a lot of efficiency in the hardware supply chain. It also increases points of exposure, making hardware intellectual property more vulnerable. In the meantime, integrated circuits are ubiquitous, and the attackers are very capable. If a malicious party wants to tamper with or probe into our circuit, they can do that with some very advanced testing equipment for failure analysis and diagnosis purposes. They can also run sophisticated reverse engineering processes using some automated tools to extract the layout and sometimes also read data from the chip as it is up and running in the field. So with both of these, hardware IP exposures are on the rise. So let me give you a few concrete examples about the attacker's objective. One of them is counterfeiting, where the designer designs one intellectual property, but it gets pirated or cloned by some other parties. Another one is malicious modification, where another party could tamper with our design to inject some bad data to modify it so that it produces some wrong results or create a backdoor that will leak sensitive data as a user is interacting with the hardware. The final attack is fault injection, where the attacker can control the environment that the chip is running by maybe controlling the voltage, the temperature, or even forcefully inject some faults through fault injection equipment. And that can also lead to wrong results or the leakage of sensitive data. And all of them has been exploited in real world to cause significant damage, both to the IP right owner and also to the users who are using the chip. Attackers' capabilities also vary. They go from black box, where the attacker has only very limited interaction capability with the chip. Specifically, the attacker can only interact it from the intended input-output interface. So essentially, the attacker can send in some input values and learn the true outputs, but they cannot see the internal. And these capabilities goes all the way to white box capabilities, where the attacker can see everything, ranging from the structure of the circuit, the netlist, every gate and every wire and their locations and their interactions. And the attacker can also read the values anywhere, at any time, under any conditions by controlling the simulation or the execution environment. And this fully transparent attack model is the white box attack model that I'm going to emphasize on in this talk. And I'm going to present security solutions that goes both in the black box model and all the way to white box models. So as you can imagine, for any security vulnerabilities, people come up with some defenses. So here I would like to introduce 3 classic hardware defense techniques. The first one is logic locking, where the original circuit can be easily pirated. So what we do is we lock it. We lock it using a secret key. And this secret key will control some modifications that is known as key gate. So by modifying the original netlist through the insertion of key gates and the introduction of the key inputs, now we can control the functionalities by putting different key values into the circuit. And only one of the key values will recover the original design and make the design into an operational mode once again. Another solution happens more like at the manufacturing level, where we can split the layout of a circuit into some very advanced nodes, front end of the line, those lower level transistors that needs to happen at 3 nanometer or 5 nanometer. And then separate them with some back end of the line metal connections that only needs to happen at 10 nanometers and 20 nanometers, and have them fabricated at different places, and eventually integrate them together into a working circuit. And as you can imagine, if the attacker is only coming from one of the foundries, they only know half of the designs without the other half, and therefore they again cannot pirate the circuit. The final solution is more like getting into the nitty-gritties of the reverse engineering process, where we can modify the connections between, for example, the poly layers and the metal layers, so that it's very difficult for the attacker to get into that precise level when they are going through the physical reverse engineering process, and therefore that serves as a secret that confuses the attacker. So even though these 3 solutions sound quite different, they're actually very similar in the sense that all of them are trying to deny the attacker a portion of the design that is semantically critical. Logic locking is trying to hide the secret key. Split manufacturing is trying to hide part of the routing from the malicious foundry. And IC camouflaging is trying to hide certain layout patterns from reverse engineers. And as it turns out, we can evaluate the 3 security solutions under a unified evaluation framework. And therefore, in the rest of the talk, I'm going to focus on logic locking as our main security evaluation target, because it is the most intuitive solution among the 3. So here I'm getting into the first technical solutions that we want to investigate, and that is structural vulnerabilities of logic locking. And before we go to there, let me also introduce some background about functional weakness of logic locking. This is how people traditionally evaluate the security of this solution. So they assume that the attacker has access to the lock circuit and also an oracle. So this oracle is an activated IC that someone can buy from the open market. It is functionally correct. but we assume that the attacker cannot see the internals. The key is stored in a tamper-proof and read-proof location. Therefore, the attacker can only interact with the oracle through the inputs and outputs to learn the golden outputs, the golden functional behavior. And what the attacker can do in this environment is that the attacker can query the oracle based on certain input patterns to learn the golden behavior and use that golden output behavior together with some analysis on the log circuit to figure out what is the correct key value that can give me that behavior, that correct behavior. And with a single key, it's actually very easy, right? You can just send in any patterns, maybe putting 0 and 0 into the oracle. You learn that the correct C output is a 0, and the only key value that gives you that value is going to be a 1. This is functional attacks. And what we found is that, logic logging is vulnerable not only from a functional perspective, but also from a structural perspective. Functional attacks really look at the output behavior. But as you can see, this locking key gate also modifies the structure of the circuit. And we have ways to analyze the layout patterns, or the connectivity patterns among these gates to figure out what is the key value that is the most reasonable choice to make the circuit structure reasonable. To make a better sense of that, out of that idea, let me also go over the logic logging process. Logic logging starts from the original design that came out of the design phase, and then insert additional key gates and key inputs to become the log design. And this log design supports different activation possibilities and the different key values. Again, only one of the key values is correct. And in order for us to differentiate from the attacker's perspective, the correct design versus all of these incorrect designs, we must answer this question: what is special about the correct design? And if you look at this picture, right, I already put, the correct design with the green color. The correct design is really the original design that receives a lot of optimization efforts from the design phase. Whereas all of these incorrect designs are really just arbitrarily generated circuit from an arbitrarily incorrectly configured key gates, and therefore they have never received any optimization during the design phase. And that makes the correct design stand out as the most optimal design among all of these activation possibilities. And one particular feature that we can exploit to differentiate at the optimality level is what we call the redundancy level. It measures how many of the gates in the circuit are actually doing some meaningful work. And if we compare the redundancy level from all of these activation possibilities, we will find that the correct design is the most optimal circuit with minimal redundancy level. So the circuit is quite optimal. It is also very testable, whereas all of the wrong designs, they would have a lot of untestable gates and untestable faults, meaning that many of the circuit elements are not doing any meaningful functionalities. And they not only introduce extra overhead, but they also compromise the manufacturability and testability of the circuit, making the circuits unreliable. And therefore, redundancy level is a very important indicator that can help us differentiate the correct design from the incorrect ones. Here is a more concrete example. Starting from this circuit, there are two keys that we can try, right? Key code 0, key code 1, and they will produce different circuits. If you only look at a circuit, both of them look like reasonable circuits. But once we run the redundancy level evaluation, we will see that the circuit on the right has some untestable stacked fault, which means some of the circuit elements on the top portion of the circuit can be completely removed without changing the output behavior. Whereas the other activation possibilities, when we put key equals 1, produce a fully testable circuit. Every gate in the circuit is doing some functionally meaningful work. And based on this comparison, the only reasonable deduction that we should make is that the key should be a 1 to make the circuit reasonable, right? Because the other one, if key equals 0, we wouldn't even have this circuit in the first place. So to verify the effectiveness of this attack, we first run the evaluation under different keys through a comprehensive topological analysis. We find that for many of the common two-level and multi-level structures, incorrectly configured key gate will deviate the redundancy level. It will elevate the redundancy level. But also, we have to think about a realistic attacking environment where we have not just one key gate, but a lot of key gates, maybe more than 100 key gates, and they interact with each other. We have to find a way to decompose the key space. Otherwise, we're searching a very large exponential key space, and then it's going to take a huge amount of efforts to run redundancy evaluation. So what we end up proposing is to evaluate each key bit individually at the beginning, to quickly find out some clear information and use that information to prune away different parts of the key space and eventually identifying key correlations either through some unidirectional dependency or bidirectional dependency through pairwise evaluation. And little by little, we're able to recover one big key bit at a time here, one key bit over there, and maybe two key bits over here, and sometimes key bit equivalent over there, and eventually prune away a lot of the key values. And then we're going to land with a partial key recovery with very high accuracy. So we evaluate redundancy attack against two most common logic locking methods. One of them is to insert an XOR gate, as I shown earlier from that picture. The other one is to insert a multiplex, again, using a key value to select between two different connections. We find that the accuracy goes from at least 50% in the XOR case and up to 82% on average for the multiplexers, and the precision has always been very high. So most of the key bits that we recovered are indeed correct. And remember, all of this happened without any functional knowledge. We never knew what is the true functionality of the circuit, but by just looking at the structure alone, we're able to recover a lot of the key bit values, and this provides a significant jump start for the attackers into the reverse engineering process. Redundancy attack really just stands out to be one example of structural vulnerabilities. And recently, we did a more comprehensive investigation into, given some of the other structural attacks that people come up with, what are their similarities and differences? We find that structural vulnerabilities can fall into three categories. Redundancy attack represents an optimality attack, where we measure how good a particular activation candidate fits into the lock circuit, and the correct circuit should be the best fit. There are some other structural vulnerabilities that take advantage of the regularity of the circuit. Think about a scenario like this, right? You have a circuit with 4 multiplication circuits. And if locking is only applied to one copy of this multiplication circuit, then we can use the other unprotected copies as references to figure out what is the correct way to make this locked circuit appears consistent with the other copies. And this really points out to a very sad fact, which is it's very hard to protect regular circuit, simply because there are so many reference points that people can make from one part of the circuit to the rest of the circuits. And finally, the process of inserting key gates and modifying and designing a circuit is also very predictable. There's certain two preferences from the locking algorithm and so also from the synthesis algorithms that produce repeatable and learnable patterns. And the consistency can also be measured through these tools and used as an indicator for key recovery. So what I'm trying to say over here in general is that protecting a regular circuit is difficult, and also doing modifications after the design has already been implemented also leaves a lot of optimality and predictability traces. And both of these ideas point us to a particular direction, which is we should focus more on irregular circuits, and we should embed logic locking at an early stage in the design process so that it can be better integrated with the true functional design. And that motivates our jump into the next section of this talk, which is sequential obfuscation via state space partitioning. And here we're really trying to solve some of the key dilemmas that traditional logic locking methods face by coming up with innovative ways to control key exposure and obfuscation scope. So I'll first present an abstract picture about what logic locking is actually doing. Right? Suppose we have a lot of these dots, and every dot represents a piece of functionality we're trying to protect. What traditional key gates do is that they try to protect every functionality with some key values. Right? If they fall into this region, key should be green. If they fall into that region, key should be blue, and key should be orange for the another region. And this provides a very comprehensive protection. Every piece of the functionalities are locked. However, this also produces a lot of key exposure. Whenever the attacker observes one of these functionality pieces, and then they learn the true behavior from the oracle, they can quickly determine what is the correct key value. So after a little while, they will say, well, green controls this part, blue controls that part, orange controls a different part. And after a little bit of collecting the true behavior from the oracle, the key becomes completely vulnerable. The solution to that problem is also very simple. We just don't let the key expose itself too frequently. Instead of protecting every piece of the functionality, why don't we just protect some critical pieces, right? And this partial protection makes the key a lot more resilient in the sense that if the attacker did not reach the blue region, and they can observe the true functionality from the oracle still, but that information does not allow for any key recovery. In the meantime, the downside of such an approach is that it offers minimal protection. A lot of the functionalities are unprotected, and that is also definitely not what we want. The solution to this dilemma is what we think by understanding the fact that these functionalities are not individual events, but they are known temporal execution sequences that are connected through some transitions. So think about a finite state machine. So this is the most common model that we model hardware controllers. We have some states, some transitions, and there are certain inputs that trigger the transition from one state to another, while at the same time producing some outputs. And this could represent the control sequence of a particular hardware circuit, such as, for some POS machines, right? Inserting the credit card and then moving to the next stage of authentication, and then moving to the next stage of funding transfer. So what we can do is that we know that these events happen in a particular sequence. So why don't we take into account that sequence? And then instead of controlling every piece of the functionality, we only use the key value to control certain critical points that we are transitioning from one mode to a different mode. So again, in this picture, we only need to let the key value change from blue to green, blue to orange when there's a functionality change from G to J nodes. Similarly, from B to H, we want the key to change from blue to green, to green to blue. And what is happening is that if someone is running the machine within a particular partition, let's say within the green mode, they're not really getting any knowledge about the key value, and that makes key exposure much less than before. Therefore, in summary, this will produce little functional exposure, but still every transition and every node is protected under some key values. Therefore, we can achieve still a broad obfuscation coverage. To actually realize this picture in the hardware world, there's three elements we have to implement. The first one is to implement a hardware circuit under different configurations and produce a corrupted circuit. The second one is given a particular hardware specification, find out this optimal configuration assignment that maximizes obfuscation coverage while minimizing key exposure. And the third pillar is to design these activation control mechanisms that monitors the intrinsic sequential evolution, but still invoke the external secret keys at those selective points for activation control. I'm not going to dive into all of these aspects, so I'm going to show you the most important part, which is to assign configuration by analyzing the sequential behavior of a particular state machine. So this is an actual state machine examples. We have some nodes, some transitions, and different edges. The dotted and the solid edges represent different input conditions. To find the best configuration assignment that satisfies both security and key resilience objective, we can run a minimum partitioning to find out a way to separate the graph into some different partitions while minimizing the number of links in between. And there's some well-established algorithms, such as the Kernighan-Lin algorithm, that support graph partitioning for up to 1 million nodes or multiple millions of nodes. And that is more than enough for what we need for hardware state machine partitioning. And then based on this partition result, we can assign different partitions with different configurations. And this example shows 2. We can also do multiple partitions, 3, 4, and even more. And based on that partition result, we're going to implement different nodes and transitions based on different configurations by diverting the original register transfer level specification. And eventually, everything will be converted into a shared corrupted circuit. As a result, the balanced partition provide a very strong obfuscation strength because, whenever the attacker reaches any node, there's a high probability that the key value needs to be answered, right? There's no dominant key value that can recover a lot of functionalities. While in the meantime, minimum cut minimizes the key exposure points, therefore enhancing key security. And the mechanism for controlling this key mutation is through a circuit that determines whether we should hold or maintain the previous key value, or we should toggle to a different key values. And this function will be controlled by a combination of the intrinsic state and transition information, but also the externally supplied key inputs. And in the actual implementation, the function can be implemented in many different ways. We can use a lookup table, we can use a field programmable array, FPGA, or we can even use a key controlled point function such as a Hamming distance comparator. And again, this is actually another real FSM examples and with a real partition result. As you can see, I'm highlighting essentially what is the obfuscation coverage between the traditional solutions using logic locking, traditional key gates based obfuscation versus the Janus obfuscation we propose based on these partitioning ideas. On average, we can achieve a more than 17 times improvement on the corruption scope at the same attack resilience and at the similar overhead levels. And because we are modifying the transitions, we're embedding the corruption at a higher abstraction level, they also achieve a stronger structural integration to make the solution structurally resilient. So that concludes the second topic I want to talk about, which is, using these partitioning ideas and making advantage of the intrinsic transition patterns to expand the obfuscation scope while maintaining the obfuscation coverage. That's very nice in the black box and gray box model, because there's still the secret key that controls the activation, and we assume that is secure. The attacker cannot see that. It is stored in some tamper-proof and read-proof memory. However, if we actually look into some real-world attackers, right, someone coming from a fabrication facilities, they have this state-of-the-art electro-optical microscope. They have different ways of observing values structurally, and also by observing side channel behaviors, electromagnetic fields, the power dissipation, and with many of these physical interaction with the chip, the attacker has more visibilities than what we traditionally assume. And that is the white box attack model I want to highlight. In white box attack model, the attacker can see everything from the circuit, going from the structure of the netlist to the value that the chip is executing at the runtime. For example, there's a paper called "The Key is Left Under the Mat," and this paper points out that even with some non-invasive probing equipment that is relatively cheap, with like $1 million, that is a lot cheaper than the actual probing device from a foundry, the attacker can extract the key value while it is being loaded from the key register into the circuit. And this really violates the entire assumption of key security that is really the foundation of logic logging and logic obfuscation. And we believe indeed semiconductor attackers' capabilities are close to a white box, and physical key extraction can be achieved using relatively inexpensive ways of probing. So in this scenario, the attacker can really see everything. They can see the structure, they can see the value, they can see what is happening. They can even control the execution environment to run the circuit under whatever condition they want through fault injection. So the question is, in this scenario, is there anything we can do? Right? Can we still do some protection? Well, we can. And in the hardware domain, people have not been doing that. But in the software domain, this fully visible attack model is what people have been operating with when they're developing software obfuscation techniques. Right? If you look at what software developers have been doing, they have been obfuscating their code using some very involutive transformations. And the goal of this obfuscation is usually to preserve the functionality while making it harder to reverse engineer, to analyze. And, for example, you can remove all the comments from your code. You can transform the control flow to eliminate some obvious functional pointers. And these are some standard software obfuscation techniques. You can share binary instead of the source code. And all of these obfuscation solutions, they're not trying to lock the circuit. They're not trying to protect against direct cloning. Rather, they're trying to prevent someone from understanding the functionality of the code so that they can run some more involutive reverse engineering attacks. And we want to bridge that idea also into the hardware protection realm. In the hardware world, there are also some hard problems that people have identified through so many years of designing, synthesizing, and analyzing circuits. One of these examples of hard problem is to analyze RTL behavior from a lower level gate level circuit. Usually, people design circuit by writing some RTL code in Verilog or VHDL, and then run them through some automatic tools to generate a netlist. But once we're given a netlist, going backwards is very difficult. Analyzing sequential behavior in particular requires a lot of computational resources. So given there's this one-way function that happens in hardware analysis, we ask ourselves this problem. Can we leverage this difficulty to build some obfuscation solutions so that, again, we are maintaining the functionality, we're preserving the functional correctness, while making the attacker's life a lot more difficult in reverse engineering? I'll again start from a more concrete gate-level reverse engineering examples. So let's say the attacker is given a gate-level circuit as a foundry, right? They need this for manufacturing. And what the attacker can do to reverse engineer it is the attacker can just put any value into the circuit, run through the circuit, run through the evaluation of all of the gates to learn the correct behavior. And that translates into a very specific reverse engineering goal on the right-hand side. That is, the attacker can learn the functionality of a sensitive state immediately by running a combinational analysis of the circuit, simply because everything is fully visible. They don't even have to run the circuit. They can run the circuit in a simulation environment with full observability and controllability. As a result, this is a very simple reverse engineer attack that is nonetheless very powerful. Our defensive goal would be to make such an analysis as difficult as a much more complicated sequential analysis. We don't want the attacker to just get into the circuit, run a very quick analysis to learn the functionality. Rather, we want the attacker to run some complicated reasoning before they can learn any piece of the functionality in the reverse engineering process. So how do we do that? Well, the ideal solution would be we lock every piece of the functionality with a different key, right? In that case, every key is only used once. And even in the white box attack model, when the attacker learns one key at the beginning, they can now use that same key value to activate the rest of the circuit. So again, now in this picture, if the attacker wants to learn the functionality of this, target state on the right with a purple key, it has to go through a lot of the transitions, through sometimes hundreds or even thousands of cycles before they can learn the true functionality. And that multi-cycle analysis takes a lot of takes a lot of reasoning efforts, making the attacker's life a lot more difficult. But this is only the ideal picture. The real question is, how do we store so many keys in the hardware? It's going to be super expensive. We don't have the resource to store thousands or millions of the keys and then allow them to be easily communicated with the chip. So what we have to do is to think about a mechanism to produce these keys securely, again, in the white box attack model. And our solution is to hide the keys within the sequential execution patterns, essentially bind the key generation with some sequential execution patterns, and then use that to intrinsically generate the keys. So that arbitrary recovery becomes computationally expensive. And that is, again, a pretty abstract picture. I'll give you more concrete examples. So these keys can be defined to be a function of the state transition history. Taking any state as an example, as you can see, I'm putting a function on top showing what is the information that goes into this key generation function. For every state, we can assign it with a key value that represents a signature from its past transition history. And as you can see, we can use these key values to encrypt the circuit at the design time and also decrypt them at the execution times. The keys don't have to be externally provided. As someone is running the circuit little by little, according to this legally defined transition sequence, we can design a function that just picks up these key state encodings and transition information little by little, and then roll them into a key mechanism, essentially generating very complex signatures. I use those signatures to control the activation of the circuit. And this really meets that one-way requirement that is necessary to build the security solutions. In terms of key assignments, the attacker, the designer has visibility to this FSM diagram. They can analyze the transition patterns, they can analyze the relations among these different nodes. Therefore, making key assignments is a relatively easy task for the designer. However, from the attacker's perspective, remember, the attacker cannot see this picture. They can only see a sea of gates and wires at the gate level. And for them to make this sequential reasoning, they need to unroll the circuit into multiple cycles, run a very complicated Boolean satisfiability or maybe testability analysis to find this real transition pattern. And that would take a huge amount of computational resources. And this disparity in the difficulty is what allows us to build efficient security solutions that complicates the life of reverse engineering attackers. So at the implementation level, this is what that picture translates into. This is a standard model of sequential circuit. We have some combinational logic, we have inputs and outputs, and also some flip-flops. What we're adding is some key mechanisms to control the functionality. So we're going to use some key registers to control the activation for any of the behavior that the combinational logic produces, including the output and the state transition behaviors. But these keys are not static. They are generated by reading values from the original design. So at every cycle, we read some value from the original circuit, use that together with a key mutation function to update the key value. So the key is constantly mutated to meet what they were assigned in the original design phase, and then this constantly mutating key will be used for activation. And as you can see, there's really no static secret that controls the entire activation, and that is really what makes this solution white box secure. there's no single point of vulnerability. No single key can be used to unlock more than one piece of the functionality. And it may appear to be, a quite straightforward solutions, and it is indeed very straightforward in the single pass FSM diagram. But in reality, there are a lot of constraints. Specifically, we're often dealing with some graphs with some complicated transition patterns with cycles and reconversions. And many of these cycles require a consistent activation, right? For example, at the execution time, whenever we reach S2, we must make sure that they all produce the same key value. And that puts a lot of burdens on how we assign the key values and the state encodings. And we actually explored a lot of different ways, different functions that we can use to assign the key mutation functions. Without looking into the details, really the idea is that some of the basic functions, such as using only an XOR function and read the state encoding to update the key value, is an evolution function. The evolution function puts a lot of constraints on what we need for effective key mutation. And sometimes they go in conflict with the basic requirement of FSM implementation, which is every state requires a different key value. And eventually, we come up with this non-evolutionary, but that is nonetheless reversible function to support a more effective key mutation while eliminating constraints on the state encoding. We actually come with some additional solutions to handle some more specific scenarios, such as parallel paths, by, for example, duplicating a node or using a more than minimum width state encoding so that we can leave some of the extension bits to not impact the key values and therefore allow multiple states to share the same key mutation effects. And furthermore, in addition to the state level control through state encoding, we have also proposed a limited transition level control by allowing certain transitions to maintain their previous key values. And this turns out to be a very effective lever to address constraints in such a tight graph when the key needs to converge with a very short path. And with the several solutions, of course, we also need some algorithmic framework to incorporate them so that we can solve arbitrary graphs. We put them in a particular priority orders, and then we run breadth first traversal through the original graph. So starting from the original graph on the left, we run a bunch of transformations to preserve equivalence while also extracting a bunch of symbolic formulas that are necessary for key consistency. So these symbolic formulas are represented by a bunch of binary vectors and their correlations through XOR and rotation. And it precisely captures what needs to happen in terms of the binary encoding values and the binary key values to achieve key consistency. And after that, we send these formulas into a formal solvers based on Boolean satisfiability to find the optimal key assignments while taking this rotation behavior into account. And that will give us all of the binary encodings and binary keys. We can then use them to XOR encrypt every transition, every state to produce an obfuscated FSM. Send this obfuscated version for synthesis to produce a locked circuit, and then assembly it with the rest of the components, the key registers, the traditional state elements, and also the key mutation functions to realize self-activation. And as a result, everything is self-contained. There's no external activation lever, but when the attacker looks at this obfuscating implementation, all they can see is a locked logic, and to actually make sense out of it, they have to run some complicated sequential reasoning to learn the true key evolution. So within that picture, the attacker can no longer run combinational analysis because they need the key information. And the key is really a function of sequential traversal. So the attacker needs to run some sequential analysis to figure out the key for any target state that they want to recover. So to evaluate the attack resilience, we measure how long it takes for the attacker to learn to extract the key values for a particular state that happens at a particular execution depth. Many of these sequential machines that we analyze have a depth of 200 cycles. So going from the initial state to a target state would take more than 200 cycles. What we found that is sometimes these sequential solvers are still quite capable, but they can hardly go beyond 50, or in the best case, they cannot go beyond 100 cycles. So there are a lot of states that sit at a depth that is more than 100 cycles that cannot be easily reached. So the attacker would have a very hard time learning their functionalities, even after days of running these very capable Boolean satisfiability solvers. And there are even other benefits that I didn't mention earlier, such as the original design containing unspecified transitions, and they can also serve as some additional traps to confuse the attacker and leading to incorrect reverse engineering outcomes. So that serves as an additional layer of additional level of barriers to prevent reverse engineering. And by carefully evaluating the trade-offs among different, key mutation strategies and different architectural solutions, we're able to limit the overhead to somewhere, less than 20% in area, less than 14% in power, that is the most critical level, and less than 20% in delay. Even though these numbers may sound still relatively high for hardware implementation, I want to point out that this is a pure control protection mechanisms. Any circuit consists of some data path elements and some control elements. The control elements is usually less than 1% of the area, and they also do not sit on the critical path. Nonetheless, they represent the most valuable intellectual property because this is really the custom design that the designer puts together to cooperate the interaction of a bunch of other more standard than regular data path components. So controller is the one that is worth protection, and it is also relatively small to start with, therefore making it more tolerable to some relatively higher overhead. If we look at these overhead numbers from the whole chip area, it's going to be less than 2%. So that's some of the security games that I've done in the past, going from structural vulnerabilities to some partition idea to increase the obfuscation scope, to think about possible reverse engineering solutions in the fully transparent attack models. I also want to spend this last bit of the talk in talking about some reliability solutions. In particular, I want to talk about a way to enhance the effectiveness of error detection by taking advantage of some temporal properties. Errors happen in hardware, right? Whether that comes from some manufacturing defects or some radiations that the chip is suffering, or some aging effects, right? As you get a smartphone, you use it for 5 years or 10 years, it might start malfunction simply because of aging. So failure happens in any hardware, and failures in controllers is the most critical because controllers handles the overall operation of the device. And to detect errors, people have come with a quite standard framework using error detection codes. The idea is to run the original computation, but in the meantime, design a very simple predictor to produce a property that we can verify. An example for that is parity code. We can use some XOR parity to protect the data to build this additional redundancy so that any violation to that parity property indicates some errors, and therefore we can use that to detect errors. This solution can also be put into protecting finite state machines by, for example, putting additional parity bits into the state encoding as shown on the right. And we can use a simple tracker to do these parity computations through XOR, maybe through some nonlinear parity tracks to detect error. Well, if you think about parity, it is actually a very efficient solution for protecting data. You have a 10-bit data, you want to add a 1-bit parity, it's going to incur a 10% storage overhead. But if you have a 10-bit flip-flop, and if you want to put a 1-bit parity, the overhead for the circuit implementation is much higher because we're not just storing the data, we're actually using those data for computation. If you increase the width of the data storage, simultaneously, we also need to increase the size of the combinational logic that talks to this data, and that leads to a much higher overhead. And that makes traditional error detection code a very ineffective and costly solution for enhancing FSM resilience, reliability. Another problem with traditional error detection code is that they really provide only a one-shot detection opportunity. If error happens, and if we're unlucky, we land at another undetectable state, that means we just coincidentally went from one place to another valid state without going through any valid transitions. Starting from that point, any of the execution will go out of synchronization with the correct behavior, but we would never have a chance to detect it because functionally, or in terms of the correctness of the parity, everything will appear correct starting from that point, even though functionally it has already diverted from the original execution trajectory. So this is really the dilemma that traditional error detection code faces. They have only a single chance of detecting errors, and within any limited overhead and power constraint, we cannot embed many parity bits, so we will only have a pretty low error detection probability. To solve that problem, I would like to propose this ideal picture, which is we can design some randomization trap. And this randomization trap essentially means whenever there's an error that is not immediately detected, it will enter this trap to receive some randomization effect. You essentially go from a random code to another random code. And because of randomization, we would have another chance of detecting the error in the subsequent cycle. And because it is a trap, there's a large likelihood that we're going to remain in the trap. And this allows for continuous error detection possibilities in subsequent cycles. So as the machine is executing every cycle, we will gain one additional effective parity bits, eventually achieving a very high detection probability, but by only embedding maybe a single parity bit at low overhead. The question is, how do we design this randomization trap? Well, we actually already have a way to do that based on our previous solution on white box logic obfuscation. You see, white box logic obfuscation intrinsically corrupt or randomize the circuit. If there's a mismatch between the encoding and the key values, they need to match to activate the circuit. And if they don't match, decryption will happen using a wrong key. Therefore, the transition will be diverted to a random wrong place. And that is exactly the randomization mode that we want in that error detection picture. More importantly, in the white box logic obfuscation part, we were solving some constraints through symbolic formulas and Boolean satisfiabilities to make these key values and state encodings satisfy a certain property. But there are often still some wiggle rooms to accommodate additional constraints. What I mean by that is, in addition to letting these binary values satisfying the requirements for white box logic obfuscation, we can embed some additional parity constraints. As I illustrated in this picture, these key values and encodings satisfy not only the key consistency constraints, but they also satisfy a 1-bit parity constraints. And the wiggle room can even be wide enough to accommodate even more parity constraints. This is another example. Again, it's a perfectly valid white box logic obfuscation solution, but there are two parity equations that we can evaluate and measure based on these encodings and keys for error detection purpose. What is happening at the architecture level is really based on that traditional FSM execution picture. We're imposing additional constraints on the state elements, both for key consistency and for parity purposes. And all of them are superimposed in the same place. So without additional overhead, we're able to satisfy both security and additional reliability needs. So here's we can run some mathematical equations to evaluate exactly how much error detection benefits we're getting out of one parity bit, but by combining that with some temporal evolution. What we found is that eventually one parity bit, and then through the corruption supported by white box obfuscation, we can effectively achieve k-1 effective parity bits, where k is the state encoding. And that is really the most we can do given any error detection code. Even with a bounded error detection latency, without letting it run until infinito, we would approximately getting k-2 effective parity bits. That is, again, much more than a single parity bit that people can typically embed within a limited overhead. What about if we embed additional parity bits? If we go from 1 parity bit to 2 parity bits, we're getting a little bit of benefits in terms of error detection probabilities, but we are also gaining a lot of benefits in terms of error detection latency, because 2 parity bit would give you a 75% detection probability in the first cycle and 87.5 in the second cycle, etc., etc. Here's a quick peek into the experimental result. Eventually, this reports, the reliability benefits in terms of effective parity widths versus the area overhead, and all of the red dots represent traditional solutions. Blue dots represent our solution by integrating error detection code with sequential evolution supported by white box logic obfuscation. As you can see, most of these blue dots sit at Pareto optimal points compared to traditional solutions, meaning that, for example, at the same overhead level, they can achieve a much higher error detection effectiveness. And again, even though this is a temporally enhanced error detection, we found that, again, even with a single parity bit, we achieve an average latency in less than 1 cycle. So this is a very quick and efficient solution, given the fact that it combines some temporal behavior. It takes some temporal behavior into account. So to conclude this talk, security and reliability is really not just about solving those security and reliability problems, but also taking usability and practicality into concern. We must consider not only functional weakness, but also structural weakness and even physical weakness in the white box attack model. We need to think about novel defense objectives that can be realized that, even with some very powerful attackers, there are some, equivalence preserving transformation that can be done to enable transformation, to enable white box security while preserving the usability and functional correctness. And finally, by exploring some algorithmic perspective of the design space, we can learn that some efficient solutions and low implementation overhead while carrying out all of the security and reliability benefits at the same time. So with that said, that's the end of my talk. Thank you very much for attending.
Thank you so very much, Leon. That was a fascinating talk. A lot of very interesting topics. I didn't expect a lot of graph algorithms to show up in a talk like this. Hardware security is not all that far away from what we do in computer science. So that was fascinating to see. I wish we had more time. We do not. I will allow a quick question or two quick ones maybe, and make sure that students to complete the feedback. I wish we had more time, Leon. This was really great. If you don't mind, I can invite you when we do the summer workshop, inside the summer workshop, if you are in town, so you could go into one.
Yeah, I'll be here in the summer. I would like to.
Yeah, so I'll talk to you about that, because I think there are a lot of fascinating things. So while people think about the question, since I mentioned graph partitioning, that was completely unexpected. Graph partitioning is a very common problem in many areas in scientific computing, parallel processing, and so on. Just quickly, is the graph that you work with, I know they were like states, and so I don't expect it to be a very large graph, but if you were to do ambitious in the context that you do, how big can the graphs get? Like, so to begin with.
These controllers in real world runs for somewhere between a few hundred states to a few thousand states, and sometimes even hundreds of thousands of states.
So that means the graph partitioning problem can theoretically be solved exactly, because it's an NP-hard problem, so people would go with heuristics and so on. So you probably would afford even for an exact algorithm. Is that important for you?
Yeah, we're using some heuristic algorithms like Kernighan-Lin algorithms as an efficient partitioning. They can support some parallel analysis. Eventually, we're able to run this partitioning even for hundreds of thousands of nodes within a few minutes. So that's very efficient. Yeah.
Okay.
And I would also like to follow up briefly about this interaction between software and hardware. I think there's a lot of overlap, both at the algorithm level and also in the principle level. I think there's some intersection between software security and cryptography and hardware, such as one-wayness and building obfuscation. And this is really happening in all of these three fields. We should really borrow some of their principles in hardware protection, because software security has evolved for dozens of years. Cryptography provides some formal guarantees. So all of these are nice things to incorporate into the hardware world.
I completely agree. And I knew this intuitively, but not as striking way, the way you did now. The direction of the states, like the graph is directed, right? Is that an issue for when you partition? Do you pay attention to the direction, or it doesn't matter?
It doesn't matter. Yeah,
okay.
We treat it as
so you think of it just like another undirected graph, and you want to minimize how many cuts you have, basically, right?
That's right. And we also developed some custom partitioning algorithm to not minimize cut, but minimize the number of nodes that are entering into a partition. And that is, related to some of the encoding tricks that we play with to further reduce the overhead.
Okay. I'm going to see if there is anybody who has got a quick question, but we will have to round it up here because it's finished time, and I know students have to go to class, but we would like to have you back, Leon, for the summer workshop. I will be in touch with you. Please share your slides so we can put them up, and we'll put the recording on the CIDR website. Other than that, I think thank you very much for attending, everyone, today, and have a great finishing up of the semester, and good luck with your exams. The summer workshop will happen in May 18th to 22nd, that 1 week. And so James has shared information for you to let us know whether you'll be attending or not. Those of you who are in first year CIDR students are required. Bernie, if you have a question quickly for Leon, we can take your question.
I
have
was
a
just going
question?
to thank you, Leon, for a great seminar, and we look forward to having you in the summer workshop. I'll be there.
Yeah,
Yeah,
wonderful.
awesome. Thank you very much.
Yeah, this was great, Leon. Wonderful. I think I don't want to hold people more. So thank you very much. And we will be in touch. Otherwise, I'll see you at the summer workshop, everyone. Those of you who are first year students, especially. All right. Thank you. Bye-bye.